A building is millions of decisions stacked on top of each other. And almost every catastrophic failure in history comes down to just one of them. A single detail, small enough to miss, fatal enough to bring down everything above it. I'm an architect. These are buildings that failed not because the idea was impossible, but because one tiny thing was overlooked. A column made thinner, a calculation no one reran, a number a computer got wrong, a pile of dirt. Each one is now written into the codes that keep your building standing. The smallest details, the biggest failures, and the lessons that rewrote the rules. Here's how an architect actually looks at a building. Forget the facade. What I see is a load path, an unbroken line that every kilo of weight has to travel from the roof, down through the bones, into the ground. And that line is only ever as strong as its single weakest junction. One connection, one column, one weld. In a small thing, a weak point is an inconvenience. In a large building, a weak point is a countdown. So when something gets changed on site, quietly, reasonably, to make the job easier, the only question that matters is whether anyone retraced that line. Usually no one did. Watch. On the 29th of June, 1995, the Sampoong department store in Seoul collapsed, completely, in about 20 seconds. 502 dead, 6 missing, 937 injured. It remains South Korea's worst peacetime disaster. And it is the purest one-detail story I know, because the building was killed by changes, each one small, each one signed off. It was designed as a 4-story office block. The owner turned it into a department store during construction. To fit the escalators, planned support beams were removed. Then a 5th floor was added, for a restaurant strip and, originally, a roller skating rink. Then the heavy refrigerated air conditioning units on the roof were dragged across it to a new position when neighbors complained about the noise. Now watch the detail. This was a flat slab building, floors resting directly on columns, no beams. The single most important number in that system is the slab's resistance to punching shear, whether a column will punch straight up through the floor it's holding, like a pen through paper. The columns supporting that top floor and roof were built 600 millimeters across instead of the 800 the calculations assumed, quietly slimmer, to make room. Cracks opened in the 5th floor ceiling that April. On the final morning, they widened by the hour. Managers shut the top floor, but kept the store open because it was a busy day and they didn't want to lose the takings. At 5:52 p.m. the roof punched through, and 5 floors pancaked into the basement. Every change was small. Together, they removed the structure. On the 29th of August, 1907, the south arm of the Quebec Bridge, being built to be the longest cantilever span on Earth, folded into the St. Lawrence River in about 15 seconds. 75 of the 86 men on the span were killed. 33 of them were Mohawk steelworkers from the Quebec Reserve. The detail here isn't a thing you can hold. It's a number nobody updated. The consulting engineer, Theodore Cooper, was the most respected bridge man in America, and remote, working from New York, rarely on site. Early on, the span was lengthened to save the cost of a pier. That change made the bridge heavier. Its own dead weight grew well beyond what the design assumed. Cooper did not require the dead load to be recalculated. The bridge was, quietly, carrying more of itself than anyone had checked it could. And the place that load landed was the lower compression cords, the giant members being squeezed along the bottom of the arm. Their lattice lacing, the small diagonal stitching that keeps a slender compression member from buckling sideways, was under-designed for the real load. Days before the collapse, those cords were seen bending. Deflection in one growing from 3/4 of an inch to over 2 inches in a week. Work continued while engineers debated by telegram. Then cord A9 buckled, and 20,000 tons of steel went into the river. A second collapse in 1916 killed 13 more when the new central span fell during lifting. Out of it came the engineer's iron ring. a reminder worn on the working hand. The detail was some left unredone. On the 23rd of August, 1991, a vast concrete oil platform base was being slowly lowered into a Norwegian fjord for a final test. At about 65 meters down, there was a low rumble, then a roar. A wall failed, the structure flooded and sank, and hit the seabed hard enough to register as a magnitude 3 tremor. No one died. It was a controlled ballasting operation. But the loss was around $700 million, and the cause is the most modern detail on this list. A number a computer got wrong that no human checked. The base was built from 24 enormous concrete cells. Between every 3 round cells sits a small triangular void called a tricell, and the tricell walls hold back the sea pressure trying to crush in. To design it, engineers ran a finite element model. The concrete split into around 23,000 elements, the computer solving the forces in each. But the model was too coarse exactly where it mattered, at the sharp corner of the tricell. It underestimated the shear force there by around 47%. It reported barely half the real load. So the tricell joint was never designed as its own problem. It got the same modest reinforcement as a plain wall, with bars detailed so they couldn't even grip properly in the corner. The wall was built to survive a load that was, in reality, nearly twice as large. At 65 meters of water pressure, it tore. The lesson rewrote how the industry trusts its software. A model is a confident guess, and the one place you most need it right is the one place it's hardest to mesh. The detail was a corner the computer couldn't see. On the 27th of June, 2009, in Shanghai, a brand new 13-story apartment building did something buildings almost never do. It fell over. Not pancaked, not crumbled. It tipped as one rigid block and lay down almost intact in the mud. One worker inside was killed. The photographs are unforgettable precisely because the building looks fine, just horizontal. And the detail that did it is almost insultingly simple. Dirt on the wrong side of a hole at the wrong time. On one side of the building, crews were digging a pit for an underground garage. On the other side, they piled the excavated earth, a mound reported around 10 meters high. Picture the forces. The building sat on slender hollow piles, which are superb at carrying weight straight down but weak against sideways push. On one face you now had a deep open pit, removing the soil that braced the piles. On the opposite face you had a heavy mound, pressing sideways into the ground. That difference created a lateral pressure across the foundation that no one had designed those piles to take. The ground beneath shifted, water from a neighboring creek seeped in and softened it, and the whole footing rotated. The piles snapped at the base like carrots. The structure of the building above was, by all accounts, fine. It was never the issue. The failure was entirely in what they did to the ground, a temporary site decision about where to put the spoil. The detail was a pile of dirt nobody added up. At 4:15 in the morning on the 17th of January, 1978, the roof of the Hartford Civic Center arena collapsed into the seats below. 6 hours earlier, around 5,000 people had been inside, watching basketball. The timing is the only mercy in this story. The roof was a vast space frame, a lattice of steel rods meant to share load across the whole grid, and its design was a triumph of computer analysis over engineering judgment. The model said it was safe. But the model didn't account for one uncommon failure mode: the way a long, slender compression rod can buckle sideways well before it's overloaded on paper. And the as-built frame quietly omitted bracing the original design had specified, leaving some exterior rods braced only half as often as intended, so they were far longer and far weaker than the calculation assumed. Some members ended up overloaded by hundreds of percent. Here's the part that haunts me. The physical structure had been screaming the truth for months. Workers reported visible bowing in the roof during construction. People raised it. And the answer, again and again, was that the computer said it was fine. The engineer trusted the model over his own eyes and the eyes of the men on the steel. Then a heavy, wet snow load landed on it. Modest, well within what the roof should have carried, and the whole grid came down in seconds. One omitted brace, multiplied across a grid, against a buckling mode the computer was never asked about. The detail was a warning everyone could see and chose not to believe. In March 1981, the 5-story Harbor K condominium in Cocoa Beach, Florida collapsed during construction, the whole frame, in seconds, while crews were placing concrete on the roof. 11 workers were killed, dozens injured, and the investigators found something that's hard to believe of a real, permitted building, a check that was simply never done. It was a flat-plate building, the same beamless slabs-on-columns family as Sampoong. And for that system, there is one non-negotiable calculation: punching-shear, the question of whether a column punches up through its slab. On Harbor K, by the official finding, no punching-shear check was ever performed for the floor slabs at all. The single most basic test in flat-plate design skipped. And the numbers underneath made it worse. The slabs were built about 8 inches thick where code wanted closer to 11. The reinforcing steel, the bars that fight punching, sat too high in the slab, which shrinks the slab's effective depth, the only dimension that actually resists the punch. Thinner than it looked, weaker than it looked. The terrible thing is that this exact failure mode had killed people a decade earlier, in another flat-plate building, and the lesson hadn't carried. When the fresh concrete went onto the roof, a slab punched through at a column, and the load it dropped overwhelmed the floor beneath, which dropped onto the next, a vertical chain to the ground. The detail was a single calculation nobody ran, on the one check the whole system depends on. On the 25th of January, 1971, 2/3 of a 16-story apartment building under construction in Boston fell, top to bottom, floor onto floor, in a progressive collapse. 4 workers died. This one is a useful bookend, because it shows how many small failures can line up behind a single trigger. The investigation found a whole cascade of them. There was no proper building permit. The concrete in places had reached as little as 700 psi where 3,000 was specified, barely a quarter of its required strength. The temporary shoring, holding the fresh floors up while they cured, was struck too early, and the wrong reinforcing bars were placed in critical spots because 2 different bars carried the same confusing mark on the drawings. Any one of those is serious, but the trigger, the place it actually started, was a single point, a punching-shear failure at one column connection, inadequately designed and then loaded before the cold-retarded concrete had gained the strength to take it. One column let go. The slab it held dropped onto the floor below, which wasn't designed to catch a falling floor, so that one dropped too. Floor onto floor onto floor, a vertical domino run from roof to basement, in seconds. Notice the shape of it. A building doesn't need 100 things to be wrong to come down. It needs one connection to fail with no second path for the load. The detail was a single overlooked column, and a structure with nothing to stop the fall once it began. Look at what actually killed each of these. A column quietly made thinner. A dead load some left unredone. A shear force a computer got wrong by half. A pile of dirt on the wrong side. A brace left off the drawings. A punching check never run. Not one of them failed because the building was impossible to make. They failed in the gap between the perfect design and the finished structure. The gap where a fabricator improvises, an owner changes the use, a number goes unchecked, a model is trusted over the steel. And almost everyone could have been caught by a single competent set of eyes, on site, asking one question: what does this change cost in strength? That's the real lesson buried in all of them. So here's the test I'll leave you with. Next time you stand in something huge, a mall, an arena, a tower, don't look at the size. Look for the load path and ask what the single weakest junction is and whether anyone rechecked it after the last change on site. Because in a big building there is no small detail. The thing you overlook is load-bearing. This channel is full of these, the world taken apart and explained honestly, above ground and below. If that's your kind of thing, stick around. I'll keep drawing them.